I will present our work, Learning to See and Act, Task-Aware Virtual View Exploration for Robotic Manipulation. Our goal is to make vision-language robotic manipulation policies more robust under occlusion and visual distribution shifts. Many robotic manipulation methods use vision-language models as the backbone. However, real scenes are rarely clean or stable. The target object or end effector can be occluded. Lighting, tabletop appearance, background texture, distractors, and camera poses can all change. Our key question is whether the policy really understands the task or whether it overfits to fixed observations from the training distribution. To study these challenges systematically, we extend RLBench and build RLBench-OG. It contains two suites. The occlusion suite has two protocols. Occlusion 1 trains and tests under occlusion, while occlusion 2 trains without occlusion and transfers directly to occluded test scenes. The generalization suite changes lighting, tabletop color and texture, background appearance, unseen distractor objects, and camera poses. Together, these protocols evaluate occlusion resistance, robustness, and out-of-distribution adaptability. To address these challenges, we propose Task-Aware Virtual View Exploration, or TVVE. The model uses RGBD observations from wrist and front cameras, the instruction, proprioception, and a task ID. The first component is a multi-viewpoint exploration policy. It performs coarse grounding to locate the key interaction region, then selects 3 virtual viewpoints for re-rendering, which recovers information hidden by occlusion. The second component is TaskMoE, which routes visual features according to task and scene context. The final policy combines multi-view images, point clouds, and task information to predict position, rotation, gripper state, and collision. This slide shows how MVEP is trained. Searching over camera poses is a large action space, so we use 3 stages. First, we pre-train with a fixed strong viewpoint to obtain a stable manipulation policy. Second, we use PPO to optimize viewpoint exploration. The reward combines task reward, confidence reward, and view diversity reward, so the policy learns informative and complementary views. Third, supervised post-training aligns the learned viewpoint policy with action prediction. The visualization shows that under occlusion, MVEP produces views with higher information gain and improves decisions. The second component is Task-Aware Mixture of Experts, or TaskMoE. It addresses generalization in multitask manipulation. A single shared encoder, or routing based only on task ID, can suffer from task interference. TaskMoE uses the instruction, task ID, and visual features as routing conditions, and selects experts through a task router and gates. This encourages semantically similar tasks to share parameters without simply increasing experts for every task. The TSNE and expert usage maps show that different experts specialize in different visual semantic patterns. Here are the main results. On RLBench-18, TVVE outperforms dense models that rely on fixed re-rendering viewpoints. It also improves over the strongest baseline, ERP, raising the average success rate from 81.6% to 86.6%. On RLBench-OG, we evaluate 10 tasks under 8 perturbation types. TVVE reaches an average success rate of 67% and consistently outperforms the baselines, showing stronger stability under occlusion and visual disturbances. The quantitative analysis validates our design choices. For virtual camera poses, we vary the radial constraint by plus or minus 20% around 0.75 to 1.3 meters. A more focused range of useful viewing distances improves performance. Increasing the number of views from 2 to 4 improves spatial perception and reduces failures from partial observability. Sampling acceleration and camera caching help control inference cost. TaskMoE also improves generalization to new tasks. Beyond simulation, we validate the method on real robotic platforms. The tests include lighting changes, tabletop and background appearance changes, occlusion during manipulation, and distractor objects. Compared with the baselines, TVVE maintains more stable execution under these disturbances, suggesting that virtual view selection and task-aware routing also help sim-to-real generalization. That concludes my presentation. More details, code, and benchmark data are available on our project page. Thank you for watching.